Graphing tips. We're going to start by refreshing our memory about a graph and how it's set up. So here we have a graph grid, and as a reminder, the horizontal axis is what is traditionally called the x-axis, and the vertical is what is traditionally called the y-axis. When graphing, typically in a science class you aren't graphing things called x and y, but something like in this table, age and half-life. Although not always, when given in a table like this, typically that first column will be your x value and the second column will be your y value. Once you have that established, the next thing you need to figure out is the scale for graphing. Ideally, you want to use as much of this graph grid as you can. So you don't want your graph just down in one little corner. You want to spread it out. So, to do that, we need to look at how many squares are available in the two directions. On this particular grid, in the x direction, we have 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13, 14, 15, 16 squares available. And our largest number in our x column is 22.5. So to figure out our scale, we take 22.5 and divide it by our number of squares available on the grid. Now if I, whoops, let me clear, I'm using a calculator here, 22.5 divided by 16 gives me 1.4. Now 1.4 is not a particularly easy number to go by. Now, general rule of thumb, you want to go by something that is multiples of 2 or 5 or 10. So we could round up to 1.5 per square, and that seems like that would be a good scale for our x-axis. Now we can do the, let me label that, x-axis. Our y-axis, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So our largest y value is 31. So we're going to divide that by the 22 squares. And we also get 1.4. That was not intentional. So again, we're going to round that to 1.5 for our y-axis. So I went ahead and labeled my axes, cleared everything else out of here. So if it's 1.5 per square, it's going to be 3 for every other square. And because my stylus that I'm using to do this isn't fine tipped, I would not be able to label every square on this one. So finally, we get to graph. So our x-axis is our age. Our y-axis is our ratio. So now we're ready to graph. So our first pair is 0, 0. So that's going to go down here in the corner. 4.5 and 1. So 4.5 is going to be halfway between the 3 and 6 right here on our x-axis. 1 is a little less than 1 square's worth, because remember it's 1.5 per square. So I'm trying to put a little dot roughly where that would go. 9 and 3, got that. 13.5, that's going to be at our halfway point here. And 7, the next square after 6 would be 7.5, so a little below that. 18 and 15, 18 and 15. And 22.5, that's halfway between the 21 and 23. And 31, a little below the line between 30 and 33. So notice our points do not make a straight line. Not every graph is going to be a straight line. In this case, it's going to be a nice curve. Half-Life has this nice curve to it. So we're going to essentially try to connect our dots with a nice curve as best we can, which will allow us to interpolate in between. Now, again, I'm using a stylus. It's not as easy as pencil on paper, but you get the general idea. So that's identifying our axes and setting up the scale. Let's look at a couple others. Here's our next set of data. We've got distance for our x-axis and velocity for our y-axis. So again, we need to set up our scale. Recall that on our x-axis, this is the same graph grid, we had 16 squares. So for our x-axis, 16 divided by 16 is 1. So that's going to be our x scale. That's going to be an easy one. Our y-axis, we have 22 squares. So 1,500 divided by 22 is 68.2. So now we have to figure out what we want to round to. Now you always want to round up, because if you round down, you're going to run out of room. So we could go by 75s, would probably, or 70s. Let's do 70 for our y scale, so that we can make that fit nicely. So let's try that, 1s and 70s. So again, I've cleared everything out. I've labeled my axes, going 2 squares at a time again because of my lack of detail in my stylus. Got my axes labeled, distance and velocity. And so now I want to plot. So 2.5 and 200. Now we're going by 70s on our vertical scale, 1s on our horizontal scale. So 2.5 is going to be half a block over from the 2. 200, 140, the next square up would be 210, so that's going to be a little below that. 5 and 500, so we go 420, the square above would be 490, so a little bit above that. 7 and 490, so that one, 7, 420, 490. 7.5 and 400, a little below the 420. 8.5 and 820, it's going to be a little below the 840, the 8.5 block. 9 and 500, 9, there's 560. So that's 490, that's going to be right around in there. 10 and 950, 840 plus 70 is 910, so that's going to be somewhere in there. 11.5 and 510, let's see, 420, 490, right around in there. 14 and a half and 750. That's 700. The next one up would be 770, so about there. And 16 and 1500. Let's see, it's going to be right up in here someplace. So now, here's a case where this is more like real data. I'm trying to darken my dots a little bit here. Where it doesn't make a nice, neat line, whether it's linear or curved. There's scatter to the data. And so when you have something like this, sometimes you're going to be asked to draw a best fit line. Now that does mean linear, so it's not going to be a curve, it's going to be a straight line. And ideally you want it to fit kind of in the middle of the data points. So, freehanding, I'm going to try to draw in a best fit straight line through my data points here. This could be disastrous. But roughly something like that. So I've got kind of an even scatter of data on either side of my line, but it shows more or less the general trend of our data. So that's drawing a best fit line through data that has scatter in it. Got one more where we're going to have scales that are going to be significantly different as far as the size, but it doesn't matter. When you're setting up your scale, we don't care that they're not going to be the same size number. They're just two different things that we're dealing with. So our x-axis, again, we've got 16 squares, our largest number. Now notice this is not in order, is 11.3. So 11.3 divided by 16 gives me 0.7. So I think in this case I'm going to just round it to 1 for my x scale. I think that will look the nicest and be easiest to work with. Now let's look at my y-axis here. It looks like 0.25 is my largest number here. We've got 22 squares, so 0.25 divided by 22 is 0.011. So I'm going to round that one to 0.02 for my y scale. So let's see what that ends up looking like. Okay, so I went ahead and filled in my scales. So on the horizontal axis we went by ones. Vertical we went by 0.02. And sometimes people get a little tricked up by the decimals. So we had 0.02, 0.04, 0.06, 0.08, 0.10, 0.12, 0.14, 0.16, 0.18, 0.20, 0.22, 0.24, 0.26, 0.28. When in doubt, just use your calculator and just keep adding whatever your scale value is to be sure that you're filling in the numbers properly. So now let's plot these points. So we've got 9 and 0.2. So go, whoa, let's erase that. Not sure what it thought I was doing there. 9, oops, and we'll erase that because I did that wrong. 9 and 0.2, not 0.02. So that's going to be right here. So there. Even I make those kinds of mistakes. 3.5 and 0.08. So 0.08 and 3.5. 1.25 and 0.025 is going to go right around in there. 5 and 0.1, it's right about there. 7.4, 0.15. 7.4, 0.12, 4.15. 11.3, somewhere between the 11 and 12, 0.25. 0.24, 0.25 is going to go in the middle-ish. 8.7, 0.19. So we got 0.16, 0.18, 0.19 right in there. 6.6, roughly 6.5, 0.15, 0.12, 0.14, 0.15. All right, so we're dealing with decimals, which is sometimes a little tricky. So you have to be careful. As you saw, even I can make these kinds of mistakes. 0.2 is not the same as 0.02. And again, we've got essentially a linear. We've got one outlier in our data set, but that's okay. We tend to ignore those. And again, here's a case where we can draw in a nice best fit straight line if we need to for a nice linear relationship. So when you're plotting data, first thing, set up your scale so that you use as much of the graph as you can. Ideally, you want to go all the way to the edges, or at least pretty close. And then when you plot your points, you're either going to draw in a curve to connect the data points, or a line. It may be a best fit line through the data points, or it may actually connect the dots. And sometimes you'll just be told, don't even bother drawing in a line. Just look at the data itself and not worry about what the actual line would look like. Because when you look at a graph like this, you can also just get a general idea of what's happening. In this case, we could say that as the distance increases, the velocity increases. General rule of thumb, when you're talking about a relationship like this, you always start with the x value and then talk about what the y value does. If you remember from math class, there's like the independent and dependent variables. The x is your independent, the y is the dependent. That part doesn't really matter. But what we typically are looking at is whatever this axis is doing, how does that affect the vertical axis? So if we had a graph, let's see, I'll have volume versus pressure. You would get a graph looking something like that. So in this case, we would say as volume increases, this is increasing volume, pressure decreases. So the pressure is dropping. So when you're talking about those kinds of relationships, always start with your x value in your statement, and then talk about what does the y value do in response to that. So that's some ideas about how to graph and also how to read a graph, how to interpret a graph. That will hopefully help you as you work your way through some of our labs.